Welcome to the BetterHealthGuy podcast, where we take a deep dive into complex chronic conditions and explore ways to build resilience, improve vitality, and achieve better health. To stay updated on Scott's work, you can sign up for his newsletter in the show notes, where you'll also find ways to support the show and help make more episodes like this one possible. If you find the podcast valuable, please subscribe, rate, or leave a review, as it helps the show reach additional listeners exploring similar questions. The content of this show is for informational purposes only and is not intended to diagnose, treat, or cure any illness or medical condition. Nothing discussed on this podcast should be considered medical advice. As always, please discuss any health-related decisions with your own personal medical authority. And now, here's Scott, your Better Health Guy.
Welcome to episode 231 of the Better Health Guy podcast. If you are seeking new ways to create better health, I might just be your guy. Today, we continue with part 2 of our discussion with Dr. Dayan Goodenowe on lipid biology, plasmalogens, and neurodegenerative prodromes. If you have not had the opportunity to listen to part 1 of our discussion in episode 230, I urge you to listen to that first, as it builds the foundation for our discussion today in part 2. We already introduced Dr. Goodenowe's bio in episode 230, so today we're going to jump right in and learn about chronic illness and neurodegenerative prodromes. And with that, here's part 2 of my interview with Dr. Dayan Goodenowe. Welcome to part 2 of my discussion with Dr. Dayan Goodenowe. We're going to talk today about neurodegenerative and other chronic illness prodromes, and just for a moment view these conditions from the Goodenowe lens, looking for more light bulb moments today from Dr. Goodenowe. I'm sure he's going to have many, so welcome back to the show, Dr. Goodenowe.
Thank you, Scott. Happy to be here.
Let's talk about a number of different conditions that many unfortunately are facing, and the prodrome or pattern or fingerprint of what you see both in your lab testing, which we're going to talk more about, but also in terms of the patterns of the contributors or root causes that are driving these conditions in the first place. And then also let's talk about how you might approach supporting someone dealing with these conditions and whether or not the plasmalogen precursors or phospholipids or other key interventions may have a role in supporting them. So before we jump in, my first question for you is, how similar or dissimilar are the chronic diseases of our modern times? I tend to think that there's probably more overlaps than differences in, let's say, a child on the spectrum, a child with PANS or PANDAS, maybe an adult with chronic Lyme or mold illness, or later Alzheimer's, MS, Parkinson's. It seems that our environment is really a key driver. The toxicity, the environmental toxicants, maybe non-native EMFs, really coming back to our terrain and the toxicity that's leading to chronic infections, immune dysregulation. We certainly have poorer food quality, nutrient density. Air and water is not ideal these days. The environment is more stressful than ever. So knowing that there are some unique properties to these conditions, do you see more similarities or more differences from your lens?
Well, there are more similarities for sure. But the first thing everyone needs to realize is that unless you're born with a genetic disease of a severe, metabolic disorder type disease, the human body is fundamentally designed to work, okay? And so these are diseases that are acquired during our lifetime. And since we acquire them, people kind of think that they were acted on us, like we have been attacked by a disease. And we think of that commonly from a bacterial infection or some other type of thing where some sort of external pathogen has infected us. And so we kind of have that natural sense of there's always a protagonist in the situation that has attacked us in terms of our health. And that's really the first philosophical fault that we fall into. And I get into that issue with autism, right? I tell people no child is born with autism. Fundamentally, a child, is a neurodevelopmental delay, okay? And so something has actually modified or reduced the health of that child. And so we talk about multiple sclerosis or Parkinson's or ALS or dementias. These are things that we have a loss of function. Okay, so some things have maybe come in that have prevented us from maintaining our health. But so we look for the bad guy. So when we talk about the similarities of, are there similar loads that are put on the human body that has caused proliferation of additional diseases? The answer is yes. And so it's kind of the canary in the coal mine, right? So you put a stress on the system, and sooner or later something's going to break. And what breaks in one person is different than what will break in another person. And I think that's the fundamental thing. So when we talk about prodromes, what we want to look at is, how have we lost resilience? And when does that resilience get lost? And when did that resilience actually cause some sort of health deviation that becomes observable in our everyday life? And I think that's the biggest challenge. And so the answer to all of these diseases is still the same thing. It's restoring health, because health is health. Like restoring health in Parkinson's or restoring health in multiple sclerosis is still restoring that individual. They may have deviated from health in a separate path, but the pathway back to health is fundamentally the same across all these diseases.
So let's start talking a little bit about aging, which some people don't think of as a disease per se, but you say that immortality is something we're born with and not something that we need to seek, that we do not acquire death, but rather we lose life. So I think a different way of looking at aging. What are the primary patterns or prodrome of what you see when someone is losing life? And how do we slow or stop the acquisition of death? What are the key indicators that you observe that suggest to you that someone is losing life? And then some of the top tools for maintaining immortality.
Yeah, so on my long list of pet peeves, this concept of calling disease and aging a disease is really, really at the top of my list. Aging is really entropy. Okay, so it's basically, our body is deeply organized, and it's an organized system. So it takes a lot of energy to maintain order in the system. So all systems try to, disperse into disorder, and that's basically the concept of entropy. And we're constantly fighting entropy to maintain order. And I tell people it's no different than in the morning, you make your bed, it looks so great, and then everything you do that day conspires to unmake your bed. You put your clothes on the bed and the bed gets wrinkled. Your dog jumps up on the bed gets wrinkled. And so what you do is you get up and you smooth the bed. So you're applying energy to the bed to restore order. Okay. And your body is doing this all day long as well. Okay. Things are happening to unmake that bed or unmake your biochemistry or create some sort of deviation from the structured equilibrium and order that the body must have to maintain its function. And we put energy in. Okay. And then energy is from calories, right? We eat carbohydrates and proteins and fats, and the body physically burns it into carbon dioxide and water, generates energy, and it then takes this energy and uses building blocks to restore the order in the human body. So as you get older, okay, you have the accumulation of opportunities for entropy to occur. It's no different than your house. Your house starts off brand new, then all of a sudden your baseboards get scuffed a little bit. Here and there you get a scar on your kitchen cabinets and so on and so forth. So 20 years later, you have a house that has all these looks messy, right? But if you repaint it and you can actually have a 1,000-year-old house that looks brand new. Okay, you can make a Model T run like it ran when it first came off the assembly line. And that is called maintenance, and it's called restoring the order. Now, people look at the human body and say, okay, well, we're not made of metal and plastic and things like that, where we don't have replacement parts in the way that the physical things in our world have. But we're actually made of biological material. We're made of cells, and these things are alive. And so they're alive and they're designed to fix themselves if we can provide them with the right materials and in the right stimulation. So aging itself, as we get older, we start losing function. We start working out less, we start exercising less. And so our bodies kind of naturally adapt to lower and lower levels of function. And when you look at that on a spectrum, you have these predictable milestones in aging. Okay. And it looks like aging is a programmed thing, but it's not. Just like if I take 1,000, cars off the assembly line at time zero and let them run, Okay, I can have a predictability. I'll say, okay, a certain percentage of the brakes will fail at X number of miles, and a certain percentage of transmissions will fail at X. And it looks highly predictable. And someone say, whoa, that car has been designed. The aging, whoever made the car, designed the car for the brakes to fail at 65,000 miles. Well, no. Okay, so different brands will have different, and so our genetics will compare. So if I compare one automobile to another automobile, there'll be differences. This one has better brakes. This one doesn't have better brakes. This one has better transmission. This one has a better engine. And so those are the genetics that we have, and these genetics give us this predisposition. So one make of model of a car might have a predisposition to bad brakes, and one car might have a predisposition to bad transmissions. And so you put the same time on both types of vehicles, and you're going to say, oh, this person gets Parkinson's. Oh, this person gets ALS. Oh, this person gets multiple sclerosis. Those are the genetic predispositions that we have because we all have a deviance. We have variability. So when it talks about the prodromes, is when we talk about biochemistry, we can very clearly understand the operating infrastructure of the human body, which is biochemistry. And so when things get deviated out of normality, low levels of plasmalogens, methyltransferase system, mitochondrial function. So there's a large list that can be bundled into a number of smaller subcategories that are really powerful indicators of, hey, here is a system that's not working properly. So for example, if your car, okay, if all of a sudden your car starts smoking, it may run for a while. You may not even know it. Like unless you're looking for smoke at the back. Okay, you say, how long can I drive a car that's smoking before the engine fails? We don't know. Some cars can go for a long time. And all of a sudden you end up with this car with a whole bunch of carbon buildup. And you say, well, that's a predictable event from the analysis of the exhaust. Same thing happens in the human body. If you're no longer processing glucose properly, okay, and you have a diabetic situation, sooner or later that's going to translate into some other negative outcome. And so the solution really is solving it at the source, and the source of virtually every single human disease is biochemical insufficiencies, the inability of the system to maintain its order. And so if it can't maintain its order, if it doesn't have the energy and it doesn't have the building material to actually maintain order, entropy is unchecked. And the entropy of the system, the disorder of the system will continue to proliferate until something breaks, until something fails.
So you've said then that the loss of life is an inability to adapt to a changing environment, and that immortality is the successful adaptation to our changing environment. So what are some of the bigger things that you see come into people's lives that lead to inabilities to adapt? Are chronic infections or toxicants in the environment or other types of stressors the things that kind of rise to the top of your list? And in addition to working to support the body's adaptability with things like plasmalogens and phospholipids and some of the other things that you mentioned, how much of a focus do we also want to put on removing or mitigating that stressor that came into our system that we're having to attempt to adapt to?
Yeah, so there are a couple of core systems. If you triage biochemistry, okay, it can be organized in a few groups. First of all, metabolic sufficiency, your ability of your body to metabolize sugars and fats, okay, right on the top of this list. So your triglyceride levels, HDL, cholesterol levels, your glucose regulation, fasting insulin, basic biochemical, can I actually process food, caloric energy efficiently? Okay, that's a core component right there. Then you move into that, and that's just the energy creation part of the body. Are you actually creating ATP efficiently, in a sense, right? And we can get a little more advanced in biomarkers of mitochondrial function, for example, which is another, like, we can look whether the mitochondria is not working properly. There's certain biomarkers that can tell us that. Then from there comes the building process. Do I have the ability to make material? And that's where your proteins and amino acids come in, your lipids. a big part of the human body is the lipid membrane. So we have 30 trillion cells. All those cells are phospholipid bilayer. And then the intra-organelle compartments are also encased in a lipid membrane. So lipids are a really huge component, and your body is constantly making membranes. Constantly, the membranes are fusing. They store, our resolvins. They store our fatty acids. They store our signaling molecules. They open up the ion channels, and they close they house our receptors and the whole nine yards. So maintaining membranes is a huge deal in the human body, which is why a lot of energy is consumed actually making cholesterol, which makes up a large portion of your membranes. Making plasmalogens, okay, is another critical building block that is physically made. Your body has what's called fatty acid synthase. So it actually will build fatty acids, especially the oleic acid and saturated fats. There's a certain number of essentials that we need, the omega-6s and the omega-3s, but your body's constantly and the methyltransferase system that make phosphatidylcholine. And so the homocysteine level. So the lipid component of health is huge. Okay. Methyltransferase system, plasmalogens, good cholesterol regulation. Those are huge drivers of the ability to maintain integrity. And your lipids are like the paint on your house. They're oxidizable. So, and just like, you have rancid butter, like the lipids are susceptible to oxidative stress. So the oxidative stress load in your body is important to manage. So you're looking at maldialdehyde, oxidized phospholipids. These things are very powerful indicators, C-reactive protein. Very simple test, right? And then from that oxidation stress, then your body recognizes it and and reacts to it. So this is where the immunological system, people look at, the immune markers like interleukin-6 and other, types of biomarkers that can tell you that. So these are very simple, straightforward measurements of understanding, is the actual physical operation system working at a basic level? Now, then on top of that, you want to say, okay, can I build reserve capacity? There is the ability to idle at equilibrium, but then there's also the ability to say, can I have a savings account? Can I push this to a level of higher levels of resilience? And this is what we work on with, B vitamins and the higher dose of plasmalogens and making sure your phosphatidylcholine levels, like animal-based phosphatidylcholine levels. So there's ways like we can cherry pick. We know there's certain areas of human health that you can get from your diet, or your body can make a certain amount of it, but it's energetically demanding. So we can actually provide some of these things, these ready-made materials, like leucine enriched, protein, niacin. Like there's very strategic ways in which we can enhance that capability. From there, then you're still a human body. Like no matter what we do biochemically, if you sit on the couch and don't do anything all day, we're not going to improve your health. So the biggest other part that people don't realize is that you have to be constantly stressing the body slightly. Okay. And it's overcoming stress. People think, oh, stress is bad. I want to live a low stress life. No, you want to live a level. You want to have stress in your life that you're able to overcome. And once you overcome one stress, you have to create another stress to overcome. And and people think of our milestones in our life of going through school, dating, getting married, having kids, getting a job, all these little lifestyle and milestones, they create a purpose and they create a challenge to be overcome. And we learn as a society how to overcome these things. And those people who can handle those kind of stresses and overcome them, they become more and more resilient. What happens though is when we get older, okay, when we get in our 50s and 60s and 70s and onward, a lot of those life milestones go away. You get empty nest syndrome, you retire, you kind of go, what am I going to do with the rest of my life? Right. And then all of a sudden those stresses and those constant challenges to overcome, like we are in motion. Our body doesn't stop. Your heart never stops. Okay. It doesn't take a break. Okay, I'm going to turn my heart off for the weekend. I'll turn it back on Monday. No, it's on all the time. Your brain is on all the time. Like there is no stopping your life. And so your life has to be continually stimulated, okay, in a way that you're challenging your body and your mind to maintain higher and higher levels of function. And if you don't do that, you're going to atrophy, and your muscles will physically weaken, your brain will physically weaken. And so you need two components of your life. You need function and purpose. You need to have a reason to get up in the morning. You have to have a positive outlook. You need to be looking to challenge your system and be invigorated by that challenge. And you have to have the biochemical sustainability to do that. And I think people forget that there's a natural lifespan that sets these milestones for us. But then if we're going to start living to 150 to 200 to 300 years of age, what are you going to do with your life? Right? Like, what are you going to do? How many years of golf can you play? Right? So you have to basically think very, very differently. And we have an incredibly pool of high functioning seniors that we can start really reinvigorating and reincorporating into our society as we go forward, which is, to me, a personal area of extreme excitement. So that's kind of where, when you talk about the longevity and people think there's the programmed cell death, there's programmed, things, those are really adaptations to lower and lower levels of function. So that's my personal take on all of this.
So it sounds like fat is where it's at. It sounds like we want some hormetic stressors that are going to be beneficial for the body. You suggest that the key technologies of immortality are to measure death and dying, to restore immortality, and to measure the structure and function of perpetual health. You say that deviation from health is unambiguous and that this is the prodrome of disease and death. So I want to talk a little bit about how you measure health with the prodrome scan and now the biometrics bioscan. How are these different? Is the prodrome scan now superseded by the bioscan? Or are they for different purposes? How would someone decide to choose one versus the other? And then what are some of the key measures or patterns that you see emerging from these tests in those people with complex chronic illnesses?
Yeah, so the difference between the prodrome scan and the biometrics bioscan is really in the depth of complexities. Okay. And so the advantage of, so the prodrome scan is simpler to interpret. Okay. It's a great place for people to start. Okay. It's going to measure your plasmalogens. It's going to measure your phosphocholeins. It's going to measure some critical inflammatory markers, methyltransferase system. Okay. So it's going to measure, probably 80% plus of what you really need. Okay. And then the bioscan goes into much more detail, and it's a little more difficult to interpret. So you need a more skilled practitioner in dealing with the bioscan. So Dr. Goodenowe perpetual health team, like all we do is bioscans because we're comfortable with that interpretation level. And then most of our practitioners still use the prodrome scan, which is simple and straightforward and gets you most of the way there, and that's just interpretive capabilities. And so there are certain biomarkers that are on the bioscan that, the sphingomyelin panel is more advanced. Some of the oxidative stress markers are more advanced. And so there's a few more advanced biomarkers on the bioscan that give you more interpretive capability. But it basically, they're really inescapable tests. Like your health is fundamentally if there's something wrong, it will find out what's biochemically, what biochemical weaknesses that you have. And then we use it for monitoring recovery. And so that's the other big difference that we do versus traditional medical work. Like we're in the research space. And so we want to look at the overall interpretation of blood samples. So we don't want to basically say, I don't want to make a determination on your health just on your cholesterol levels. Okay. Or just on your triglycerides or so on and so forth, right? Or your creatinine and those type of biomarkers. Collectively, they give you a better picture than any one. And the current medical industry is really designed for each test to have its own cutoff value and to determine yes, no, is it good, bad? Okay, where we're interested in understanding what's wrong in the system that we are trying to resolve. And then we want to fix the system. And when the fixing of the biochemical system is relatively straightforward. Like, biochemical support, methyltransferase support, plasmalogen support, phosphocholine support. Okay. So we start everyone on that basic biochemical restoration process. And we track their biochemical recovery with the bioscan and with the prodrome scan Not so we should be able to, the individual will be able to understand visually that their health is getting better. And then that should translate symptomatically in their world, that they should be feeling better, sleeping better, stronger, cognitively more enhanced, better mobility, those things.
So these tests then are looking at the key things from your lens that are impacting health and adaptability. So a lot of the lipids, methylation, mitochondria, inflammation, oxidative stress, metabolic function. I did the Prodrome scan and you and I reviewed that some time back. I'll have to put the biometrics bioscan on my Christmas list, but love these tools that you're inventing and making available for us. For someone who has not done one of these tools, the Prodrome scan or the new bioscan, are there some things that they can look at on more traditional, like LabCorp type testing that could be an indication of the potential for plasmalogen deficiency? So if we look at something like an elevation of triglycerides, does that give us any insight to say maybe it makes sense to be supporting our plasmalogens?
For sure. So fundamentally, plasmalogens, the core building blocks of plasmalogens are made in your peroxisomes. Okay. And your peroxisomes are, so you have two catabolic systems, organelles that actually break down fat. One is your mitochondria. Palmitic acid goes into there. It's a clean system. And the other one is your peroxisomes. And the breakdown of fat creates building blocks. And those building blocks are then used to make other molecules. The mitochondria is fundamentally catabolic. It basically goes in pure, it's supposed to be pure energy, basically carbon dioxide, water, and ATP. Peroxisomes are anabolic. Okay, it only does partial beta oxidation of fats, and then the partial molecules that are broken down are then used to build other things. Two of the critical things it's used to build is cholesterol and plasmalogens. Peroxisomes are also critically related to your neuromuscular system. So people who have peroxisomal issues typically have elevated triglycerides. So having said that, simple, basic, what the types of biomarkers that tend to follow each other is that people get low levels of cholesterol. If your total cholesterol is under 200, if your HDL is under 60 or under 50, okay, certainly if it's under 50, those are two indicators that you'd probably have impaired, and your triglycerides are over 100. Chances are you have compromised peroxisomal function, and chances are you will have low plasmalogens. Okay, so those things kind of go hand in hand. So typically people who have healthy plasmalogen levels naturally, they're going to have high HDL, they're going to have good total cholesterol and good HDL, and they're going to have low triglycerides. That's a general, and then your C-reactive proteins will typically be low as well. That's a good reference. The other ones you want to work on, creatinine I measure it for muscle mass. People worry about it for kidney failure, but muscle mass is another one that uric acid is a simple test that you should be having. It helps measure your NAD and some oxidative stress levels. And then homocysteine, keeping your homocysteine between, around 8 is where you want to be. So those are simple tests that can be part of all things. If those are in the wrong places, then a more important metabolic restoration is in order. You can go a little deeper.
So what I heard there that was a light bulb moment, and I got this made after our last conversation. So the light bulb moment was cholesterol below 200 may be a concern. And I see that a lot in people where their cholesterol is 140 or 150. Maybe they're on a certain type of medication and their doctor's saying, hey, yeah, it's working really well. We should keep going. But we need that cholesterol. So I think that's really, really critical, very helpful. So people can look at some of those other tests that they may have more readily accessible and see if they fit some of those patterns. We hear a lot these days in kind of the biohacking community around things like spermidine or urolithin A or NAD, a lot of the precursors like NR, NMN. There's more tests emerging in the realm of NAD. Wondering if you see that focus shifting any of these indicators of health that you're looking at.
I think they're interesting. The NAD, the spermidine, so spermidine is mostly for autophagy type things, like try to kill damaged cells, because it actually is a indicator of sick cells, like the polyamine system that's part of spermidine, putrescine pathways. The urolithin A, which is really related to mitochondrial fusion type aspects of it. Those are all interesting. They're kind of secondary players, though. Like they're even when people talk about resolvins and protectins type of thing, right? Your body makes these things naturally. If the system is working properly, you don't really need those. Okay, those are kind of secondary ones. NAD really is a good one though, but so the core precursor or nutrition for NAD is niacin, good old-fashioned niacin. So and NAD is critical because it's your main energy transfer molecule. So when your body burns carbohydrates, well, basically whether it's sugar or fat, it gets broken down to a molecule called acetyl-CoA. And then acetyl-CoA actually gets burned like your methane in a furnace. It burns into carbon dioxide and water inside your mitochondria. And it does it in two parts. One creates carbon dioxide and energy from the citric acid cycle or Krebs cycle. And that electron energy. So basically what you're doing is you're releasing sunlight energy. So when the sun interacts with chlorophyll in plants, it takes carbon dioxide from the atmosphere and water, and in the energy, the sunlight energy is used to make glucose. And so it's basically sunlight energy is stored in hydrocarbons from the sun. And then when we break that bonds, we release the energy. So what we're doing is we're releasing sunlight energy when we do that. And it's in the form of electrons. NAD captures that into a molecule called NADH plus. And that becomes the electricity of the human body. And that NADH plus then gets transferred to the electron transport chain. And that's when oxygen that you breathe comes in and it converts the oxygen into water. So you basically, we recreate the carbon dioxide and water that was originally used to make, glucose. So back to that NAD perspective. So niacin this is where precursors are more critical than actual molecules. Like the human body is compartmentalized. So it's not just what you eat, it's whether the molecules that you're providing the human body are getting into the cells and into the subcellular organelles that they require to get there. And that's why things like N-acetylcysteine or glutathione. Niacin is a precursor to glutathione. Niacin is a precursor to NAD, and it can kind of get inside the cells, inside the mitochondria. And so those are the kind of, and plasmalogen precursors are what we require to get into the brain. You can't get a fully intact plasmalogen, doesn't cross the blood-brain barrier, but a plasmalogen precursor can. So those are things that are so strategic biochemical engineering is important.
Okay, so now let's talk now a little bit about Alzheimer's. That's how I originally learned about your work, your book, Breaking Alzheimer's. We talked about that several years ago in episode 186. So wondering what's unique to Alzheimer's? What are the contributors? Is it infection, toxicity, inflammation, oxidative stress? Is it simply the loss of that adaptability that you talked about? What are the primary things we maybe need to remove from the body and then add back to have a really multi-pronged strategy that's focused both on root cause and on repair and restoration?
Sure. So in Alzheimer's disease, there's really only two biochemical mechanisms that matter. Okay. One of them is the omega-3 plasmalogens, DHA plasmalogen depletion of the brain. So for whatever reason, for whatever underlying causation, when the DHA plasmalogen levels in the brain get decreased, then membrane fusion is impaired. And the membrane structure, the cholesterol regulation in the membranes is impaired. So two things happen there with the plasmalogen deficiency. One, it is the direct underlying causation of amyloid accumulation in the brain. Amyloid accumulation is related to cholesterol transport system in the membranes. And so as cholesterol elevates, if your cell membranes in your brain cannot regulate the cholesterol levels, then the amyloid precursor protein is shifted from the healthy pro-neurogenesis molecule called alpha secretase to the the amylogenic pathway, which is beta secretase, which is amyloid. So that's one thing. And the second part is the actual fusion and release of neurotransmitters are directly impacted by the plasmalogen. So it affects all neurotransmitter systems. But there's one transporter system that is uniquely sensitive to disruptions in neurotransmitter release, and that is the acetylcholine system. So when acetylcholine neurons are impaired from releasing acetylcholine, the cells become starved of choline. So choline reabsorption through the choline high affinity transporter is impaired when nerve transmission is impaired. And this creates a cascade called autocannibalism. And this is where the cell membranes start to digest their membranes to make acetylcholine. And this causes membranes and cells to start shrinking. So in Alzheimer's disease, we see shrinkage of the brain. And when a cell cannot absorb choline, it has to make phosphatidylcholine from scratch. And when it does that, it does it through a system called phosphatidylethylamine N-methyltransferase. And this is a methyltransferase system. And when that gets overloaded, you get elevated levels of homocysteine, and you actually get shutdown of the whole methyltransferase system. Why that's important is that the methyltransferase system is uniquely sensitive to the neurofibrillary tangle formation in Alzheimer's. So there are two pathologies in Alzheimer's disease, which is from the name from Alois, Dr. Alzheimer himself, is these neurofibrillary tangles, which occur inside neurons, and these amyloid plaques that occur outside neurons. The plaques are directly related to the plasmalogen deficiency, and the tangles are indirectly because they're directly related to methyltransferase system. So virtually all of the neurofibrillary tangles are caused by methyltransferase defects. Because phosphorylated tau, it's the dephosphorylation of tau, and tau are called matrix-associated proteins and MAPs, and they're involved in organelle transport down axons, and it's almost like lockjaw. Like it's the phosphorylation pushes, and then the relaxation phase is the dephosphorylation. The dephosphorylation is heavily dependent upon the methyltransferase system. So when the methyltransferase system gets impaired, the lipid transport gets impaired. And this is what happened, the organelle transport in axons gets impaired. And this is critical for Parkinson's, for example.
So one of the things I think that we've heard for many years is that amyloid was a cause of Alzheimer's. And if we could just find that drug to remove it, people would no longer have Alzheimer's. I think more recently, we hear people talking about how amyloid may actually be the water to put out the fire, that it may not be bad, and we may not want to remove it if the fire is still burning. So which of those perspectives do you kind of align with? I know you mentioned that plasmalogens play a role in impacting amyloid as well. If we're using plasmalogen precursors that are potentially helping to reduce amyloid or taking the water away from the fire, could that ever make the problem worse?
Yeah, so two things. So first of all, amyloid is not causative of Alzheimer's disease, or not causative of dementia. It's clearly causative of Alzheimer's disease. It is actually the pathology that defines Alzheimer's disease. So you do not have Alzheimer's disease if you don't have plaques and tangles, period. Okay, so it's a pathological diagnosis of an unhealthy brain, but it is absolutely not causal. Like it's not actual, amyloid does not create dementia. Okay, remember, Alzheimer's disease and Alzheimer's dementia are two separate things. Dementia is a functional assessment of brain activity. Can the brain actually do certain functions? Can it remember names? Can it count numbers? It's actually physically, how quickly can you run a 100-meter race? It's a functional aspect of the brain. Amyloid and tau are indicators that the brain is unhealthy. So the question is what is the underlying causation of the amyloid formation? That is important. Okay. Removing amyloid itself is irrelevant. And I don't fall into the category that it is a protective mechanism. I just think it is a system that is overwhelmed. the body makes more amyloid than it can clear. So the brain gets unhealthy, the amyloid precursor protein processing gets shifted, excess A beta 42 gets formed, and the brain has limited ability to remove it, and it accumulates. It's as simple as that. And even the large pathology studies in the 90s clearly showed that the amyloid plaques themselves were not toxic. And the tau formation, or the phosphorylated tau or neurofilaments tangles, likewise, okay, they definitely cause, they're definitely more, I would say, pathogenic, not pathogenic, they're more directly related to axonal dysfunction, simply because these neurofilaments tangles occur inside the neurons. So when you have tangle formation inside the neurons, it is absolutely disrupting the capability of that neuron to perform its function. But again, the issue now is the system, they kind of form in the dendrite region versus the axonal region typically. So anyways, long story short. So in that regard, the amyloid removal from a hypothesis perspective had low probability of having success. This is why it took years and years and years and years. So just for clarity, we have had multiple technologies with verifiable amyloid removal capability. Okay, this is not just one time. It didn't take just one company to identify, oh, here's how we remove amyloid. We've been able to remove amyloid, I can't think, probably in the early 2000s. Okay, but the problem is none of those trials ever worked. And even the trial now, the drug that's been approved that lowers amyloid, it still just delays the progression. You know, you'll even see 18 months before they even notice that it's actually delayed anything at all. And you have to get 4 MRIs during the process to make sure that you don't have brain bleeds. So it's very clear that amyloid is not the driving factor. Whatever underlying biochemical system that is leading to amyloid accumulation is definitely something to work on, and that is where the plasmalogens come in. And we've shown that people with postmortem brain samples with people who have high levels of DHA plasmalogens in their brain have low levels of amyloid. In the blood, in cell culture and in other systems, clearly we can modify the amyloid accumulation based upon the plasmalogen levels.
Let's touch briefly on the acetylcholine, the choline conversation. So are there other cholines besides phosphatidylcholine that play a role in brain health, in that acetylcholine system, in supporting our neurons? Is regular choline important? How about CDP choline or alpha GPC? How do we support that presynaptic neuron to support acetylcholine and neuronal health and optimize that choline and choline recycling so that we don't have shrinkage of our neurons over time?
Yeah, so choline is a critical molecule. Okay. It was discovered, I can't remember, in the 30s and 40s that it was an essential nutrient, but it wasn't actually recognized as an essential nutrient until the 90s. So that's how slow science can work sometimes. Choline deficiencies are one of the only reproducible causations of cancer known. If you eat a choline deficient diet, you will get cancer, period. Okay, it's a leading cause of liver and pancreatic cancer type situation. So dietary choline is critical. Your body can make choline from scratch, but it is energetically demanding. It's this methyltransferase system, like I was mentioning to you, is a key driver of it. So getting choline in your diet is important. So now the question is what are the best sources of choline nutritionally? So alpha GPC, citicholine, these are all fine. Okay, there's no issues with them. But really the best source of choline in your diet is phosphatidylcholine and from animal sources. Okay, eggs, meat, liver type thing. That is by far, and because it comes with other fats associated with it. And if you get good choline-rich fat in your diet, because that's the best source of choline going forward. Because getting it into the brain, like alpha GPC definitely has some good things associated with it for sure. Okay, it's a simple source. People take choline and it'll be in some of their supplements sometimes. But really phosphatidylcholine is the best way to get in the brain because it enters the brain through the lysophosphatidylcholine system, and then it's more readily available because the primary goal of choline is making membranes, but also making acetylcholine. But acetylcholine is just in that high affinity transporter range.
And do the plasmalogen precursors play some role then in the production of acetylcholine as well?
Only insofar as it improves the membrane fusion process, and it causes the release of acetylcholine, and then the reabsorption is easier, but not so it's indirect, not direct.
In the past few years, in the realm of Alzheimer's, there's some newer markers that are being used, such as p-tau217, GFAP or glial fibrillary acidic protein, NFL or neurofilament light chain, and then the A-beta 42/40 ratio. You mentioned A-beta 42 already. Has anyone looked at how plasmalogen N3 or N9 might impact these markers that we're exploring now in the realm of cognitive function? Would we expect to see any improvement in those markers from the plasmalogen precursors?
That's a really good question. We don't have direct large enough scale data to support one way or the other on that one. We do have anecdotal, so the neurofilament light chain is a really powerful marker. Okay. It's one of the more accurate ones of axonal integrity, especially for MS and ALS and things like that. And so we've seen in our clients that number come down quite dramatically. The GFAP is a marker of astrogliosis or microgliosis, and so it's an inflammatory marker. It's a little less precise. It bounces around a little bit in the different studies. It's a little more. It's not as a robust marker. And then the p-tau17, A-beta 142s. These are all they've been studied for decades and decades and decades, and so they're really more linked to these therapies than diagnosis. They're clearly present. Okay, so the p-tau has always fundamentally outperformed the amyloid markers, and I think there is value in the p-tau markers for sure.
I want to talk a little bit about brain volumetric changes. So in the realm of our listening community with mold illness or SIRS, there is the NeuroQuant MRI, which is volumetric, looking at patterns of inflammation or hypertrophy, and swelling and degeneration or atrophy or shrinkage. Some people then are using VIP as a nasal spray to help kind of improve those volumetric indicators. Wondering if you can talk to us a little bit about your personal exploration into brain atrophy over the past few years, how you reversed it, and could plasmalogen precursors have a supportive role in both hypertrophy and atrophy that we're seeing in something like the NeuroQuant? And then I know you also, building on that, now have a neuro MRI. So wondering how that might be different from something like NeuroQuant.
Yeah, so the volumetrics of the brain, you have to be very careful with, because the brain can swell and shrink from water, okay? And so the volumetrics doesn't tell you the quality or the density of that brain material. Okay, so if you're looking at the volume of your hippocampus, you're looking at the volume of your ventricles, right? And so those are clearly measures of shrinkage. Certainly ventricular size grows with age dramatically, okay? And that's it. Those are good markers, but they're really not intervenable markers, okay? And so they're very, I would say, crude in a sense. The critical markers that you want that are sensitive to structural brain recovery is cortical thickness, okay? So brain volumes, you look at the volume, they look at the MRI is looking at basically slight areas of cerebrospinal fluid in between regions, and you get some ability to define a three-dimensional space on the MRI. But what's happening inside that volume is what's really important. What's the density of that matter? What's the axonal density? What's the inflammatory density of those cells? So the outer part of your cortex is a thin band of gray matter, and it's called and you can get cortical thickness, which is different than your volumes, because your volumes are going to contain gray and white matter. So cortical thickness is a critical component. It's much, much more sensitive to functional change in your body. The second one is the density. For white matter, diffusion tensor imaging is important, but even more advanced is called neurite orientation, dispersion, and density indexing, NODI. And that gives us the ability for the first time to really measure axons and cell bodies and free water in each voxel of the brain, if you will, each three-dimensional space. And so when we're looking at And then blood flow, which is we measure by arterial spin labeling. We're looking at vascular reactivity with BOLD. Understanding the health of the brain goes much deeper. So I think the volumetrics are very crude in a sense that they tell you where you are, like, you're not supposed to, but they don't tell you quality. And each of us are going to have slightly different baselines. Okay, so you want to be careful to interpret volumes without having some sort of longitudinal analysis on yourself. Because, well, we're going to have, even though there's a general brain size and general region size, your brain can have slightly different, like you could have a smaller hippocampus your whole life, for example. Okay, or you can have, and your body might be totally, your brain and connectivity. So also the connectivity is important. So I find those MRIs, they're simple, they're inexpensive, they're fast, but they can be very, very misleading. And I've done a lot of work where we look at the volumes can give you the opposite answer. For example, children with autism, they have a increased head circumference because of brain swelling. And so when you get an inflammatory syndrome, you can actually have volume increases due to inflammation of certain regions. So you got to be very careful in interpreting volumes.
So before we move away from brain and cognition, wondering if there's a role for the plasmalogen precursors in people that have had traumatic brain injuries. Maybe you're on a road to CTE, already developing CTE. How do we support the brain in cases where physical brain injury was a driver?
Yeah, so all brain injuries. So whether it's your multiple sclerosis or Parkinson's or your age-associated cognitive decline, a concussion, COVID infection. So when the brain gets injured, okay, it has to get fixed from the inside. And so the metabolic demand on the brain, because the brain is fundamentally made of fat. So it's got to make its own cholesterol. None of the cholesterol in your blood reaches the brain. It's got to make its own plasmalogens. It's got to make a lot of its own phosphatidylcholine. You can get some of it from the blood supply. So whenever the brain gets injured, and so the mitochondrial function, those things all happen inside the brain. And if the brain gets under stress, either from a concussion or from a metabolic insufficiency or from a toxic exposure, then it has to have some level of resilience. Now, it's not sitting there with a bunch of stored capacity because the brain is working all day long. Okay. It's like, okay, I'm working full time. And all of a sudden now I got to take care of my parents. And I'm going, how do I take care of my parents while I'm still working full time? So the brain is working full time, and then it's created a load on this system. So it's got to do two jobs. It's okay, I can't work all day long and take care of my parents. So now I got to find a way to do both things. The brain has the same thing happens. So what you have to do is be able to create the level of support in that brain. So plasmalogen precursors are critical. Plasmalogen precursors and phosphatidylcholine, good methyltransferase support. Those are the things that you really need to improve brain structure and function. Mitochondrial support, N-acetylcysteine, carnitine. But typically the missing link for a lot of this is plasmalogens. And when we do that, we see, like, so for multiple sclerosis, people think of these lesions, but there's what we call the normal appearing white matter, areas of the brain that don't show up as a lesion on a T2 flare MRI, for example. Well, that's still not normal in an MS patient. So we want to watch, we don't want to look at just the lesion of the person with MS. We want to say, why was your brain weak enough to cause those lesions in the first place? So let's look at the places where you don't have lesions, and let's make sure that those areas are reinforced and strong and recovered. And that's where the advanced MRI allows us to do. For concussion recovery, for myself, I've been able to reverse brain aging. So we are definitely at the point where we can reverse. When people talk about the escape velocity for longevity, we have technically reached that in the human brain. We can actually stop the aging of the brain, and we have reversed the aging of the brain. So as I get older, my brain is now getting younger. And this is with strategic biochemical insertion, and that is the plasmalogen precursors, absolutely. Both the omega-9 for the white matter recovery and the omega-3s for the gray matter and synaptic activation. And then, of course, environmental stimulation and the biochemical support for the mitochondrial function. Absolutely. So concussion is a big, big deal. And then we want to increase the blood flow to the brain. We want to measure that type of activity. So yes, plasmalogen precursors are absolutely critical for concussions and and so on and so forth.
I don't want to go too far down this path, but since you brought it up several times, what are the key things that we're implementing to support the optimization of the methyltransferase system?
So methyl B12, methylfolate, trimethylglycine, okay, those are the big things, okay? Then the N-acetylcysteine, which actually prevents your depletion of methionine. So methionine is your critical molecule, but I don't really recommend people, you want a good protein source that gives you some methionine, but your body should be fine with its methionine. If you are cysteine deficient, your body can start losing its methionine. So N-acetylcysteine is a critical indirect support of the methyltransferase system as well. And then, of course, phosphatidylcholine, animal-based phosphatidylcholine for the brain. Creatine is also a big methyltransferase load on the body. So people need to be taking that 4 to 5 grams a day of creatine, and that will help reduce the methyltransferase load. So it gives your methyltransferase system enough room to do other things.
So for people listening, when we talk about methyltransferase here, we're really talking about methylation.
Yes.
I want to talk now about long COVID and get your lens on long COVID. There are people that think there is persistence of SARS-CoV-2 in the gut, in other areas of the body. There's people certainly that talk about clotting and endothelial damage. There's the reactivation of things like Epstein-Barr virus, Lyme, Bartonella, other infections potentially. What do you see as kind of the drivers of long COVID? And how are some of the solutions that we're talking about in the lipid realm, the plasmalogen realm, how might those be helpful with people dealing with long COVID? And then is there a component of needing to bind and remove spike proteins when we're talking about people that are dealing with these chronic conditions?
Yeah, there's about 4 things to think about here. So first of all, in the area of long COVID, the problem with the mRNA vaccines and things is that they've created the ability for cells to make spike protein, but not kill the cell. So we've been able to have cells that continually produce spike protein. So long after the infection is gone, long after the immune system is actually reacting to a toxic cell, that cell is still pumping out spike protein. And that spike protein, so there's clearly evidence that there is this chronic spike protein exposure in some individuals. Okay, so the question is, where is it coming from? So clearly the body's there's cells making this stuff. Now the spike protein itself is a mitochondrial toxin. So it goes in, it affects complex 1 of the electron transport chain. So it's clearly reducing mitochondrial function in the human body. So that the core component of long COVID and all of the even acute COVID and long-term COVID is all related to mitochondrial dysfunction and knocking mitochondrial function down. This is also why we have turbo cancers. So for example, when the mitochondrial function gets impaired, the cells start creating ATP outside the mitochondria. So mitochondrial dysfunction is core to all types of cancers. Well, when you get this extra mitochondrial ATP production, the body doesn't stay in the fasting state very well. So you get these plasmalogen deficiencies. So COVID is heavily related to plasmalogen deficiencies. So mitochondrial dysfunction is a core. From that, you get inflammation. Okay. And then you get a chronic inflammatory syndrome from COVID because mitochondrial function isn't working. You get oxidative stress. And so now you have this hyperimmune activation that creates a further stress on the body. Clearly, the brain is being affected. All this brain fog that people have with long COVID is because we have microglial inflammation of the brain. So all these things are swirling around in the COVID scenario. So the question is, how do you recover from long COVID? And there's 2 components of it. One, regardless of whether or not you remove the spike protein or there's some tools and technology. I'm not the best expert in the world on that. The other part is, can we enable the body to recover and regenerate and even thrive in the presence of the spike protein? Can we enhance the mitochondrial function? And can we restore membrane structure and function with mitochondrial support supplementation and plasmalogens and phosphatidylcholine? Okay, the lipid restoration process. Now that will get you out of the recovery problem. Okay, so your system is now back to normal. But the problem with long COVID is that the body has now adapted to this lower level of mitochondrial function. Okay, it's the equivalent of being locked in a room for 2 years. The body has to be retrained and reactivated. Okay, and so your mitochondrial function has to be brought back up, and that is a little more difficult. And getting booster cables putting on your mitochondrial function, and that's where the omega-3s come in. Like the DHA plasmalogens are quite stimulating, and then slowly building up your energetic resilience is a process. And so that's kind of where the long COVID thing comes in. Restoring brain structure and function, that part is all biochemical.
The other big challenge that many people had in the COVID era was myocarditis. And we know that the heart is high in plasmalogens. So, does increasing plasmalogens then have the potential to reverse myocarditis? And do we lose plasmalogens in heart cells in an attempt to put out the fire or chronic inflammation that's happening in the body?
Yeah, absolutely. So, the heart, 50% of the heart membranes are plasmalogens. And when the heart gets under kind of oxidative stress, it starts dumping plasmalogens out of the membrane to neutralize peroxides. So your plasmalogens are one of your most, if not the most used antioxidant in the human body, because you have lots of it. All your membranes contain this. And normally you can dump these plasmalogens out of the membrane, put out the fire, and then the body can slowly rebuild the plasmalogens back up in their membranes. But if this fire burns too long, then all of a sudden the plasmalogens get depleted to a level that the body says, I cannot spare any more of these things. And so you're now at this chronic deficient level of plasmalogens that you just can't catch up. So without the plasmalogen supplementation, and you can't get ahead of this. And so the C-reactive proteins and all that stuff. So absolutely, people with myocarditis, heart improvement in structure and function on the plasmalogen precursors is something that we see quite a bit.
So just a quick detour, since we're talking here about long COVID and thus the endothelial, the clotting aspect of this. One of our listeners, and I'm very interested as well, was wondering about when we think about strokes being connected to thicker hypercoagulated blood or clots, or maybe in some cases blood that's too thin. Talk to us a little bit about what people should be thinking about to either avoid or maximize recovery after a stroke.
Yeah, so fundamentally a stroke, most strokes are not hemorrhagic, they're more ischemic. And so those are strokes caused by a temporary restriction in blood flow and oxygenation to a part of your brain fundamentally. So it's an oxygen blockade. And so you get this area of oxygen deprivation. And what happens then is so obviously what's leading up to that is atherosclerotic type situations. You get thickening of artery walls, you get thinning of the the capillary orifices are thinner. The flexibility of the endothelium and the muscle lining is impaired. So that's all related to oxidative stress, and it's all related to oxidized phospholipids, like on that area, the inability of the endothelial level to relax. So the vasodilation capability, your ability of your heart and the relay mechanism, the baroreflex process through your brain and your parasympathetic system gets all impaired in that system. So that's an acetylcholine system. So yes, so the plasmalogen deficiency leads directly to this vascular stiffness, if you will. Okay. Specifically the omega-3 plasmalogens. So two things. One is pre-stroke, okay, these molecules, having a healthy mitochondrial, healthy lipid composition is going to, good HDL levels will help help remove the soft plaque from the atherosclerotic regions of your endothelial layer. And then the plasmalogen itself improve the vasodilation rate. All that stuff is important, okay, in order to maintain vascular structure before you get a stroke. Now, after you get a stroke, you get extreme oxidative stress in those areas of the brain that had blockage. And that's where N-acetylcysteine and carnitine N-acetylcysteine, carnitine, niacin, riboflavin, even thiamine, plasmalogens. These are all required to help that region of the stroke survive under those conditions. then there needs to be revascularization, whether or not that blockage gets opened temporarily or a secondary blood flow starts supporting that region that's been blocked.
I want to talk now about ME/CFS, or myalgic encephalomyelitis, chronic fatigue syndrome. I think one of the things that we've kind of maybe a benefit of the pandemic is now there's some renewed focus on conditions like ME/CFS and chronic Lyme disease that in the past people were gaslit and largely told it was a psychiatric condition. More recently in the ME/CFS realm, there was a study that showed that a high percentage of people with chronic fatigue syndrome also tested positive for vector-borne infections such as Bartonella and Babesia. It's also been suggested that the ME/CFS population has a high mold and mycotoxin exposure as well. So wondering what you see, maybe it's very similar to long COVID, but what do you see as the prodrome of ME/CFS? What are the contributors and what are some of the key solutions to support the ME/CFS community?
So first of all fatigue is related to mitochondrial insufficiency, period, full stop. Okay, if you have fatigue, you have impaired mitochondrial function, full stop. And you think about it, so what causes mitochondrial overload? Why? And so you get the flu or you get a cold. So every time you get sick, a big thing that a comorbidity of every single sickness is fatigue. You lie in bed, you're tired. Why are you tired when you have a flu? Okay, what causes you to be tired when you're sick? Well, you're tired when you're sick because you have all this immune cell activation and your body is using energy to support these immune cells. So your immune system and your inflammatory system is actually consuming mitochondrial energy that would normally be available for other activities in your body. And so when you get better, okay, all of a sudden that mitochondrial load comes down. So people that are in a fatigue situation, okay, multiple sclerosis, the biggest issue with multiple sclerosis is fatigue. Okay, virtually everyone with MS has fatigue-related issues, right? And then when they start doing acetylcarnitine and a few other things, they can actually improve fatigue. So all fatigue-related activity has to be restored from mitochondrial support function, okay? Because that's where your ATP is, that's where your energy is. No matter what you do, that's what you need to come back. So now the question is, where is the balance? How much can I remove of the toxic exposure? Okay. And how much resilience can I put in? Okay. And so sometimes you can actually get enough resilience, mitochondrial boosting, if you will, okay, that can allow you to actually overcome and thrive in the presence of that toxic load. And then that will actually help remove that toxic load over time. And so that's where photobiomodulation can also come in, because photobiomodulation is actually a direct stimulator of mitochondrial function. And so if you actually have your biochemistry right, and then go from there. Like up from our personal perspective, the omega-3, like the omega-9 plasmalogens are critical early stage for resolving inflammation, getting the system from the hyper-inflammatory state into a normal state, but getting people reactivated, it's where the omega-3 plasmalogens really come in. Okay, that's where people start getting, the brain fog goes away, their energy comes back, they get moving and that kind of stuff. So, but that's kind of really where the chronic fatigue thing is. So there's always a combination of two things. How much of a load can you remove some of the mitochondrial load on your system? And two, how much can you invigorate your mitochondrial function while this is going on?
So let's then move into chronic Lyme disease and mold illness, which is the vast majority of our listeners. That was my health journey as well. So if we're thinking about some of those burdens that you were talking about that maybe we need to remove, mycotoxins, maybe some of the chronic infections, for example, should we focus first on the removal stage and trying to mitigate these insults to be successful then with our restoration strategies with lipids and plasmalogen precursors and so on? Or is it better to be doing both removal and restoration simultaneously?
Well, I would do restoration first, because often if you get sufficient restoration, you don't need to deal with it because the body will actually clear itself. Okay, because the autoimmune process is because the immune activation, whether it's against mold or Bartonella or whether it's against any kind of chronic infection, the body is not handling it very well. And so your reaction to the toxin is perpetuating the inflammatory cascade. So it's being self-perpetual. So this is what autoimmune is all about. So if you can start reducing that and you really improve the secondary inflammation. Okay, so you have the primary inflammation, and then your body's reacting to that inflammation, and your body's reaction to the inflammation is creating a secondary inflammation. And so if you can eliminate the secondary inflammation just by restoration, then sometimes the whole system can calm itself down and you don't even need to do the detox. Okay. And so I would always start with that first and then select and then add your detox in.
So I guess I shouldn't be surprised that the one choice I didn't give you is the one that you've selected. And that's why I love these conversations. So it sounds like our number one focus is on the restoration piece. I am curious, though, given that we live in this toxic world and we have exposures to pesticides and chemicals and heavy metals and now micro and nanoplastics, all of these things, besides limiting our exposures, are there any tools that you find helpful to optimize the terrain, which also then makes us less hospitable to some of these chronic infections? Do you see a role for things like EBU or plasma exchange? What are some of the things that you're thinking about? Or is the entire focus really on restoration and mitochondria so that we can respond to these insults and innately detoxify?
Yeah. There's lots of cool technologies out there, but if we take a look at our animal studies, and the people need to understand that the adaptability and the resilience of the human system is quite high. It's quite amazing. And so we do all these studies where we give animals massively bad toxins at high doses, doses that no human will ever get exposed to, right? And if we provide mitochondrial and we provide the membrane support, mostly the plasmalogen support, these toxins don't have the negative effects associated with them. So cuprazone, for example, absolute demyelination molecule, right? It's a copper chelator. It doesn't even cross the blood-brain barrier. It reproducibly causes microgliosis and astrogliosis, and then you get white matter demyelination reproducibly. Okay, if you give these animals plasmalogen precursors, you don't get any demyelination. So in the presence of a massively toxic molecule that depletes plasmalogens and causes demyelination, you can completely prevent that. Another one is MPTP causes Parkinson's. Again, it's like a paraquat type toxic molecule that reproducibly causes Parkinson's in animals. Okay, all types, mice, monkeys. If those animals are given plasmalogen precursors in advance, that toxin has no effect. And so I think the biggest issue is obviously once you are sick, you're playing catch up, right? So you're in a situation where you're saying, okay, now I got to deal with an actual acute problem. And so you have to obviously deal with that as responsibly as you can. Okay, both from a resilience perspective and whatever toxic exposure you're involved in. But realistically speaking, what we're really trying to deal with is, when we're dealing with longevity, is creating this biochemical savings account, creating this resilience in our body before we get exposed. Okay, because we're going to be living in this nasty environment. Okay, it's impossible to determine and predict what exposure you may become exposed to in the future. So the number one priority is understanding these resilience protocols and incorporate them early on, so that this is back to this entropy and aging perspective, right? It's like being able to say, okay, I am predicting, I know that there's going to be entropy enhancing circumstances. I'm going to get exposed to things in my world that are going to cause an acceleration of disorder. Okay, so I need to be thinking in advance that I need to have higher level of entropy fighting resilience. Okay, can I actually restore and rebuild faster? It's like saying, okay, you know what? I live in a fire zone. I'm going to have an extra water supply on hand in case I need it. Okay, and that's really what it is in terms of creating a biochemical resilience capacity. Saying, look, there's going to be unpredictable events in the future, and how can I build the odds in my favor that I'm going to be prepared for these events?
So you talked about how having higher levels of plasmalogens could mitigate the potentially detrimental effects of a toxin and keep us from going down the path of some damage. Do the plasmalogen precursors and increasing plasmalogens have similar potential to reverse damage after it's occurred?
Absolutely. So, and there's a level, there's a limit, right? So there's going to be like we can't completely regrow, a brain of an 80-year-old, right? So obviously earlier we catch things and there's going to be some level of recovery. Okay. And that level will be depending on the organ type, for example. Like maybe liver can go complete or the heart. But there's going to be some levels of damage that we can't fully recover from. But we can partially recover and then hold that recovery indefinitely. Okay, that's where we have to. So in terms of the brain, from a concussion perspective, or Alzheimer's or Parkinson's, right? We're never going to completely regrow back someone's substantia nigra from Parkinson's, right? And so the issue is now, can we whatever damaged cells that are still viable, can we plump them up, if you will, restore those, and they can restore their functionality, and can we make a small number of cells do the same work that a larger number of cells can do? So I've actually restored function with a smaller actual physical capacity. And then can I maintain that level of function indefinitely going forward, which is all that matters, because the body does have excess capacity. Like your brain has more volume and space than you need. A good example is that when we do brain scans of all of our elite practitioners, very, very intelligent, active, dynamic individuals, and they'll have shrunken brains from age. So clearly, okay, like nobody in their 80s and 70s are going to have it's going to have a full brain. It just doesn't happen.
I bet you will.
Well, I'm hoping now. Okay. But see, even me, I've turned my 57-year-old brain into, an early 40-year-old brain. Okay. But it's not going back to 20. Okay. It's not, it's gradually, it's getting its stable place. Like when you get a lesion in a multiple sclerosis scan, the brain has already worked around it. You're never going to fill that back in. Okay. Because the brain has stopped using it. It says, I've gone on from this. I've got another, I've pathwayed this thing. So it's I don't need it anymore. Like I've passed that point. And so once the brain shrunk a little bit, it's already figured out what it's doing. So it's not gonna. The only way you can regrow a brain is if you go back to rebirth and the regenesis of the whole system. Okay, so you can't. So that's kind of where. So yeah, there's going to be limitations, and those limitations will be region dependent. Okay, how much muscle can we recover? How much, and there are certain parts of the body that probably have much, much higher. And some of the regenerative medicine out there is really quite crazy. Like some of this wound healing, like there is some really amazing technology that's way out of my scope. Like I said, we're the fertilizer company, right? We work on understanding the basic fundamental structure of the human body, making sure the body has what it needs when it needs it. Okay. And then when you stimulate that body and you put the body in the right environment, I want to make sure that the system is capable of doing what you're asking it to do. And sometimes, and many, many times, that's all the body needs. But there's definitely going to be circumstances where you need to be going above and beyond the kind of things that we do.
And to your earlier point, fortunately, there's so many new things coming that hopefully we're getting close to that escape velocity, whereas more insults affect you and I. We have solutions faster than we do insults. So you have said that there is nothing more exciting than the impact of plasmalogens in the realm of autism. Some suggest now that as many as 1 in 12.5 boys in California will have autism. There's PANS and PANDAS affecting many kids as well. We probably didn't hear much about this condition a decade ago, and now it's become so common. So what do you see that's unique in your assessment of children with these conditions? Are any of the insults different? And what comes to the top of your list of tools that can reliably move the needle in these kids, and particularly anything in terms of speech development?
Yeah, so I think we overcomplicate a lot of diseases. That's what's happened over time in my research. And clearly this plasmalogen insufficiency is a huge contributor to our aging and disease situations. And it was completely missed our attention. Like we missed this. we focus on proteins and mitochondrial function and, N-acetylcysteines, which are all very, very valuable. Okay. Those things are all super important. We study them extensively, but they have not, like, this plasmalogen deficiency contribution to reduced health has escaped us for decades and decades and decades and decades. And so it is a core contributor. It's not the only thing, but it is definitely a rate limiting factor. So in autism, okay, it's a mitochondrial deficiency disorder to begin with, which leads to inflammation, neurological inflammation, which leads to a load. Just we talk about being chronic fatigue, for example, right? So when you get sick, you have an additional load on the body. So the body can no longer can't be focused on what it's doing. Same thing, okay? You're working full time and now you're taking care of your parents. So you've some unanticipated load has been thrust upon the system, and it can no longer focus on the one job it has at hand. Well, a developing brain has one job. It's to develop its brain. Okay, it is to learn, it is to connect, it is to become highly functioning. And if you put some external load on that brain, it's going to have difficulty doing its job, which is the normal developmental pathway. Okay. And so the inflammation that affects a child at birth, whether it's from, even birth problems, or it could be an infection, something happens, or they have a predisposition for metabolic weakness, some inflammation, some mitochondrial weakness. The myelination of the brain, which is the critical component of learning and brain development, is what gets delayed in autism. Most reproducible observation across all studies is reduced white matter integrity. And the one thing that is highly reproducible in improving early childhood brain development is exclusive breastfeeding for the first 12 months of life. Okay, and studies have shown very clearly that these plasmalogen precursors are highly present in human breast milk. And so the information is overwhelming in the sense of this white matter support, inflammation support of the brain. So in our work, and we have a neuro support program. We support, there's over 200 families. We have 95% of the parents report back to us that they're seeing improvements in their children. Okay, and in their adult children as well. Okay, so this is very clear. So, and our protocol is very simple. We focus on the omega-9 plasmalogens for remyelination at the beginning, some anti-inflammatory work with, curcuminoids. The people, clearly people are working with leucovorin, like the methyltransferase system support in autism is important for sure. And this phospholipid support, phosphatidylcholine, plasmalogens. If you do these things, and proper diet as much as you can, children actually start eating better diets. They start having a higher food variability, because, parents with autism are challenging because, the kids are challenging. And so when you go look at PANS and PANDAS, that acute hyperinflammatory state that just makes them go crazy because the brain is just inflamed, right? And they become violent and they act out, and so once you start calming them down, one of the most reproducible observations we see is aggression dramatically reduced. Okay, children, their aggressive tendencies start going down because their brain starts calming down, and as their brain starts calming down, then they start interacting with their siblings and with their parents more, and they become more engaged. And so we overthink these diseases very, very much, and so this increased incidence in autism is the fact that we live in a pro-inflammatory environment. Our environment is more inflammatory. Our nutrition, like, I'm sorry, you go down the aisle in the grocery store and you just look at the ingredients in formula, infant formula. It's horrible. And so all these things contribute to a higher risk of inflammation. And then when that happens, you you get delayed development.
In scenarios then where we want to dial back that neuroinflammation, would we consider using something like Plasmalogen N9 as a standalone tool, or would we combine that with SPMs or other fats or CBD, hinokiol, maybe some peptides? What are some other ways to bring down inflammation that you've seen clinically helpful? And does reducing neuroinflammation with a combination of tools then lead to a less rapid loss of existing plasmalogens because they're not being burned up by this inflammation?
Yeah, the challenge always is how much can you do, right? Because you're still dealing with a human being, you're dealing with a child, and the parents, can you give them a list of 20 supplements to give their child? Okay, that's not practical. And so the question is, how do you triage this? What are the things that are going to give us the most impact that you can kind of add towards going forward? Clearly, the omega-9 plasmalogens, we have a very special curcuminoid called BDMC, which we're seeing really good results. It's a very potent anti-inflammatory that crosses the blood-brain barrier, reduces inflammation of the brain. Clearly, getting some B vitamins, through whatever you can get them in their diet and food. But really, omega-9 plasmalogens, phosphatidylcholine, clearly from like an egg source, and if you can get some methyltransferase support, and you're probably 95% of the way there.
I'm sure you've talked to many parents of children with autism where the child was developing normally and a certain medical procedure might have then led to a regression. So my question is, in those scenarios, if the child had higher levels of plasmalogens, maybe have allowed them to respond more healthily to it?
Clearly, that's hypothetical and theoretical, but logically, based upon what we do know about the brain and under inflammatory stress situations, the answer would be yes. Okay. And especially for concussions, for example, getting omega-9 plasmalogens before a child gets on a soccer or hockey rink, right? I think it just makes sense. So when you're going to if you get into a high injury risk scenario, again, this concept of resilience and being prepared in advance of these circumstances. And it should start at pregnancy, right? So maternal health is where you really want to start creating the biochemical resilience in your children. And you want to continue that through the rest of life. That's kind of so the answer is clearly, we would expect that the answer to be yes.
In multiple sclerosis, there's been a lot of talk these days, lots of celebrities struggling with it. We've seen Christina Applegate, Selma Blair, a host of other people that are bringing this into the discussion more. I tend to think of MS as more environmental, potentially mold exposures, infections. We know there's some research about Epstein-Barr virus and the effect on the myelin and contributing to multiple sclerosis. It certainly has an autoimmune component. You talked about how in research models, cuprizone can induce demyelination. So that's not what we're using in people with MS. So what do you think is maybe the inducer or inducers of demyelination in multiple sclerosis? And then is this a scenario where the plasmalogen N9 would be the most appropriate to really support that myelination?
Yeah, absolutely. So multiple sclerosis breaks my heart because it's probably one of the easiest of the neurodegenerative diseases to solve. Okay. And it's so unnecessary for women, specifically with MS. So multiple sclerosis is fundamentally mitochondrial dysfunction. It's basically autism that hits a fully developed female in their midlife. Okay. So autism and multiple sclerosis are basically very similar diseases as an underlying mitochondrial insufficiency. And then what happens then is all oxidative stress comes from mitochondrial insufficiency. And then when you get this inflammatory cascade, you get peroxidated membranes. And this peroxidated membranes causes microglial activation. So this is the autoimmune cascade in MS. It stems from mitochondrial insufficiency. Now, what happens though in MS is that as you get damage to the myelin, the body, each multiple sclerosis person is going to create their own specialized immune T cells for their MS. Okay. So, and it's going to happen from the B cell formation that's what creates so there's going to be some sort of damage related epitopes from that woman or man's multiple sclerosis. And then the immune system, okay, the memory B cells are going to create a unique antibody, basically epitope for that person's multiple sclerosis. And those memory cells are going to get stored. Okay, just like any other infection. So now you have a personalized immune reaction to your MS. And then so later on, so you go into remission for a while, and some other insult happens in your life, and you get a flare-up. Well, you have a predisposed immune reaction to those systems. And it's fundamentally caused by this oxidized LDL, actually, type molecule. And I do a big lecture on MS. So the solution in MS is maintaining myelination. And the advanced MRI, we can look at not just where the lesion is, but look at what's called normal appearing white matter, which is not normal in MS. So even the normal appearing white matter in MS is less dense. So it's in a prodromal susceptibility state where it can become a lesion sometime in the future. This is why you get random lesions in MS. You can't predict where the next lesion will be because all of the normal appearing white matter kind of looks, not great. So so restoring myelination with the omega-9 plasmalogens and mitochondrial support is ground zero in MS. And it can happen early in their life. And it's like if they get their first case of optic neuritis or numbing. And so we clearly show restoration of neurological function in MS. So it breaks my heart when I see these people. And the biggest problem with MS is that it takes such a long time. So people get into this kind of comfort delusional fate. Okay, well, it's not me. It's not going to happen for a while. Okay, because it takes 20, 30 years. And so they'll live a normal life for a while, and they kind of just, only way to survive is to kind of put it out of your mind saying, okay, I got nothing I can do about it. 10 years later, you get another relapse. And so people they don't necessarily have the same sense of urgency to take care of this first and long term, like someone with later on Parkinson's or later on ALS, where it's saying, oh my goodness, okay, this is happening.
Sounds like what you were describing is essentially kind of a priming effect where then subsequent occurrences, that relapsing, remitting, but could actually then be even worse because the immune system is already in a mode where it can respond very readily.
Yeah, and the biggest, scariest thing about MS is that we have these drug therapies, these B cell depleting therapies, okay, and they are effective at reducing the relapse rate, okay? So you get much less relapses in MS. But the most disturbing part about it is it doesn't change the brain shrinkage rate, okay? So it's actually reducing the relapses, but it's not stopping the actual neurodegeneration cascade in MS at all. So it indicates that the relapse is not actually the driver, something else behind the scenes. So the relapse in the B cells is kind of like the amyloid situation in Alzheimer's disease, so people are saying, okay, now the only problem is that it tricks the MS patient into thinking that they're better when they're not. So they don't have any relapses, but long-term outcomes are still going to be not favorable.
Let's talk a little bit about Parkinson's and what's kind of different from your lens compared to, let's say, MS. I think we see more people talking now about Parkinson's. It seems like it's increasing. I used to think of it as more pesticide associated. There's certainly now more talk about microbiome associations with strep and desulfovibrio and E. coli and dental pathogens and things of that nature. You talked about MPTP induction of Parkinson's and how plasmalogen precursors could mitigate the potential damage and prevent that degeneration. So what do you see that's unique in Parkinson's? Do you think we should be looking at toxic burden? Do you think we should be looking at the microbiome? What are the key things, if they're different from what we've talked about, that could be helpful to improve someone dealing with Parkinson's?
Yeah, Parkinson's most likely is 100% some level of toxic exposure, okay? Because it's affecting a very specific cell system. The problem is you don't know which toxin you got exposed to or when you got exposed to it, okay? You could be exposed to it 20 years ago. So you need You only need about 20% of your substantia nigra to be functioning for you to have normal movement. So a very significant amount of loss needs to occur before we see symptoms. So you can imagine in your 20s and 30s, you could have been exposed to something that knocked 50% of your substantia nigra down and you would never know it. Then the concept of aging kind of plays in. So now aging starts catching up to you when you're in 60s and 70s and 80s. And all of a sudden now the general brain degeneration is occurring. And this is releasing or it's causing the Parkinsonian insult that you suffered 20 years ago to reveal itself, whereas before it was not revealed. And so I think, and that's where it becomes challenging. It's unlikely that a 70-year-old with Parkinson's got toxic exposure in the last 2 years that gave him Parkinson's. Okay. Chances are it was some sort of cumulative thing that happened over a period of time. And then the aging process has kind of kicked in and slowly, and that's been the canary in the coal mine. So the problem now is going, from a it's highly likely that there was some level of toxic exposure. The solution now, of course, it's L-DOPA therapy. We can enhance dopaminergic function, but it's dangerous, not so much dangerous. The problem is dopamine is used for multiple purposes in the body. So we have a lot of secondary problems with dopamine replacement therapy, which is basically L-DOPA, because impulse control gets affected in other areas. So the goal, our strategy in Parkinson's is to, minimize the toxicity of L-DOPA. If someone is getting L-DOPA and it's working for them, we want to make sure we can keep them on the lowest dose possible and if not, actually eliminate the L-DOPA. We've been very effective at getting a lot of people off their L-DOPA completely by just using round numbers. Say you need 20% of the substantia nigra to be functioning, and now it comes down to 18%, and all of a sudden you're seeing small symptoms. Okay, well, we don't need to go to 100%. We just need to get you back up to 22%. Okay, so how much dopaminergic function can we restore and maintain? Back to this whole shrinkage and restoration. And then if we can stimulate neurite growth, so where that smaller number of cells can perform a higher function and maintain that higher level of function. And so there's two parts. So one is the inflammatory component. Methyltransferase is critical. Okay, Parkinson's is fundamentally a tauopathy type disease. So methyltransferase is a big deal in Parkinson's disease. And then the omega-3 plasmalogens, the DHA plasmalogens are specific neurogenesis stimulators. Secretory APP alpha, it actually helps neurons grow new axonal projections. And so if we can increase that innervation and let the body adjust itself, and as we've seen over time, we have a number of Parkinson's patients now that are continuing to slowly get better and better and better. Their writing is getting, like 2 years later, they're still getting better. And so this concept of the brain regeneration can take a while. My brain, at least the girls with multiple sclerosis, like she's now several years into this thing and she's continuing to get better. Okay. And so this neurogenesis, you think about your brain developing from birth to 8 years old, there's 8 years there. Okay. And so the thought that when we start talking about neurogenesis and neuro redevelopment, basically the brain is actually going to regrow or remap itself. That remapping process could take years, but it's systematically occurring. And if we can continue to stimulate that, we haven't seen the longest term outcomes at this point in time. We know we're getting this progressive improvement, and we really don't know how far that will take us. Only time will tell on that. So that's really where Parkinson's comes in.
So ALS is probably one of the conditions that people fear the most. I would say ALS and pancreatic cancer. We recently saw how quickly Eric Dane's ALS progressed and eventually passed away. And I know this is an area that you have a lot of experience with. So what's different about ALS that makes the progression so brutal and so aggressive? Is it also a toxicity? Is it an infection? Is it something neuroexcitatory? How much of a role do genetics play? And what are some of the top tools that you would consider for someone dealing with ALS? Are we getting close to the point where it becomes either manageable or even reversible?
Yeah, ALS is such a terrible disease, no question. Clearly, it is related to some level of peroxisomal toxicity. Okay, so ALS is a peroxisomal toxicity disease, first and foremost. And then within that peroxisome, what happens is an enzyme called D-amino acid oxidase becomes dysfunctional. So it is a peroxisomal disease, first and foremost, probably caused by some level of toxic exposure. Now, what makes ALS worse than other degenerative diseases is that the disease itself, this peroxisomal insufficiency that causes this D-serine or D-amino acid oxidase impairment, causes elevation of D-serine, and it basically causes hyperglutamate toxicity and activity. So that you get this glutamate and these big motor neurons, these gigantopyramid neurons become bombarded with glutamate. And the D-serine is the co-transporter at the NMDA receptor. And that D-serine is no longer regulated. So these cells just get hammered, okay? And glutamate activation gets overstimulated. That then leads intracellularly to this misfolding of superoxide dismutase. So it causes oxidative stress. So glutamate is a major mitochondrial toxin inflammatory mediator. And the superoxide anion that gets generated from this hyperactivation of the mitochondria being just bombarded, we get excessive formation of superoxide anion, which is then needs to get neutralized by this superoxide dismutase. And that protein gets misfolded. And so there's two types when you talk about genetic diseases. We're not talking about genetics for ALS. So there is a few clear linkages in ALS. If people have a mutation in D-amino acid oxidase, they get ALS very early in life. Okay, it's the most proximate to ALS of all the genetic mutations is this particular enzyme mutation, D-amino acid oxidase. So it's unambiguous what causes ALS at a biochemical level. Okay, it's without argument. Period. Okay, so the next question is now, where ALS becomes damaging is that in other neurodegenerative diseases, you get cell stress, you get cell death, fine. But in ALS, this misfolded superoxide dismutase protein gets exported, and it's no longer, it's a active toxin, right? So we talk about dominant versus recessive genetics, right? So gain of function versus loss of function. Most genetic diseases are loss of function diseases. Okay, you lose a function. You don't actually create a bad function. ALS is a gain of function toxicity. So it builds upon itself. So as the ALS progresses, it creates more and more toxins. And that this misfolded superoxide dismutase then gets spit out of the toxic cell, and it infects the cell next to it. Okay, and so it is an active toxicity, which is why it progresses so rapidly. And so that's kind of where ALS is. So our strategy on ALS, of course, is peroxisomal. The plasmalogen are very deficient. Mitochondrial. So all of this thing, it's a much more empowered. Like we push the limits much farther on the mitochondrial and peroxisomal support process. What we are struggling with, and we do have a number of successes in ALS, okay? And the question is how to maintain that success long term. It's a very, very labor-intensive disease to manage, okay, and to sustain it. And we're working on other technologies to really improve muscle mitochondria. So we got the photobiomodulation, counterpulsation. There's a few other things that we want to add to the repertoire of biochemistry that we do, and also just managing their exercise recovery. Okay, it's like starting a fire in a hurricane. They kind of got to go slow and try to, kind of protect each little spark or flame that you get as you go.
Is there an aspect of an ALS supporting protocol that also is focused on reducing glutamate?
Well, it's not so much reducing it. Well, you want to reduce it, but you want to reduce the toxicity. You want to increase the clearance of it. Okay, and so you want to be able to move it through. So leucine enrichment helps detoxify glutamate. And this is what causes some of the muscle wasting. So a lot of the work that we've done is always in neurologicals, right? Understanding the neurological brain restoration. And we are pretty comfortable that we are restoring neurological function. Okay. But in ALS, the muscle degeneration part, what we learned over time is that people thought that all of the muscle loss in ALS was due to impaired neurological function. And in our experience, we see these are two independent systems. The muscle wasting is linked, but somewhat independent of the neurological function. So once we get past the neuromuscular junction, so the neuron to neuron system in the brain and in the spinal cord, I'm pretty comfortable that we're working effectively on that. But when the motor neuron interfaces with the muscle at the neuromuscular junction, the muscle side of this equation has its own world to live in. And so the glutamate toxicity, because a muscle is not the same as a neuron. And so that is where we've been spending more time and energy on trying to reduce the muscle wasting side of that equation and glutamate toxicity. So leucine-enriched foods, ketone esters. There's some other ways that we can improve glutamate clearance is really what we want to do.
In part one of our conversation, you mentioned trehalose, a sugar.
Yep.
I first heard about that in the context of ALS from a doctor at an ILADS conference more than 10 years ago. So I'm wondering if you can talk to us a little bit about the potential benefits and mechanisms of trehalose in health optimization. And is that something you regularly use in your routine?
Yeah, we use trehalose a lot. It's a slow release glucose. It's a glucose dimer. So it's got, like where sucrose is glucose plus fructose, trehalose is nice and sweet. It's got, I think it's called an alpha bond. The two glucose molecules are released slowly. So it's very anti-diabetic. It's a prebiotic. It helps bifidobacteria basically grow in your stomach, in your gut, which is great. And so it can be it reduces the glycemic load or index. So reducing glucose, see, ALS is in a hypermetabolic state. So one of the biggest challenges with ALS is they lose muscle, but they actually lose weight. Okay, so their caloric demand is actually quite high. It's a very strange disease in that they eat way more calories and still lose weight. So they're in this hypermetabolic state. The trehalose isn't kind of a glucose, I would say that's not a glucose blocker. It suppresses an acute glucose load. And glucose itself it promotes glucose is co-transported with glutamate. So excess glucose causes it exacerbates the ALS, which is why type 2 diabetes, people that are insensitive to glucose, that actually reduces their ALS risk. So a type 2 diabetic, which basically is glucose insensitive, it actually is beneficial, which is why the diet for ALS patients, a high fat protein diet, low glucose diet is favored in a ketogenic diet is favored in a lot of people with ALS.
So briefly then, building on glucose, so many people that are dealing with metabolic syndrome, diabetes, is there a connection between levels of plasmalogens and some of those metabolic syndrome conditions?
Not so much directly, more so in the peroxisomal side. Okay, so plasmalogens are peroxisomally stimulating. So diabetes, glucose control is fundamentally a mitochondrial issue because the cells, okay, all diabetes or glucose metabolism insufficiency, so insulin sensitivity issues, that the cells, all your cells in your body absorb two types of energy molecules. They absorb free fatty acids or they add glucose. So when you are in the fed state, after you eat a meal, your blood will have high levels of glucose in it and low levels of fatty acids, but high levels of triacylglycerol, so fat. So your blood could actually be white with fat because your body is actually converting glucose, converting free fatty acids into triglycerides, and it's sending them to your fat cells for later, okay? So your body does not process much fat energy during the fed state, except your brain and your muscles. Okay, your muscles use fat, and your heart almost uses fat all the time, like fatty acids. Then when you get into your fasting state, because remember, so when you look at diabetes, you're looking at fasting glucose, right? You're not looking at fed glucose, you're looking at your fasting glucose levels. So now you're getting your fasting state after you've finished eating your meal, and your glucose levels are supposed to come down. And your fat cells are now releasing triglycerides, but they're actually releasing free fatty acids into your bloodstream. So your body now switches from using glucose for energy to using free fatty acids for energy. So when you lose muscle mass and you lose peroxisomal function, your body doesn't process free fatty acids anymore. It can't process it. There's too much of it. So when these go into your cells, you got a certain amount of glucose coming in, you got a certain amount of free fatty acids coming in, you got all this free fatty acid coming in, and there's no capacity to process glucose. So the body says, hey, I'm all full. I can't take any more glucose. So it shuts down absorbing glucose. Your glucose levels go up. So type 2 diabetes. So when you increasing fat metabolism, peroxisomal functions, this is why maintaining muscle mass, exercise, okay, time restricted eating, these things all are very, very positive outcomes in diabetes, the type 2 diabetes, basically. And so that's kind of where, so plasmalogens stimulate peroxisomal function. Okay, so a lot of them are plasmalogen, are peroxisomal stimulators, especially the omega-3s, like the DHA plasmalogens will have a peroxisomal stimulating effect to them. And so they can help lower triglycerides. So anything that helps lower triglycerides will help your diabetes.
You have said that every day you do the work you do is like living in a toy store. What can we expect to see coming from the toy store of Goodenowe in the future?
Well, the goal is making things simple, right? Infrastructure wise. Okay, so we have we get the MRI technology, we have the blood testing technology, the supplementation, the biochemical restoration, making it simple in a packaged process so people can just, go on with their lives, basically. Here's what you deal with. And then we're adding other critical modalities. I think the photobiomodulation is an important addition to our program. Having infrastructure more locally, like building centers across the country, because MRIs, right now you got to fly to California to get an MRI done. We're setting up the infrastructure in Canada. Our community health program. I'm very passionate about community public health and incorporating this type of mindset. We have to improve health. Our healthcare expenditures and the healthcare economics are crippling our infrastructure. Okay, these excessive high-priced drugs that are coming through the marketplace, we can't afford them, like the Alzheimer's drugs and these. So it's creating a huge drag. So we need to improve health. We need to reduce the load on our system. And that means incorporating it into community and into lifestyle and into mechanisms that larger populations can implement, rather than just all of us experts working with these, a subclass of our population that is motivated, interested in this. So we need to start making this type of technology more accessible to the general public. And that's kind of where my passion is in the future.
So we don't all have to come to Moose Jaw.
Right. Well, it's a great place to come. You're all welcome.
You have generously offered a discount for your Prodrome products. I'll put that in the show notes for people that want to explore that further. My last question is the same for every guest, and that is, what are some of the key things that you do on a daily basis in support of your own health?
Yeah, so it's rinse and repeat. So I have a supplement protocol I run every day. Like I have my omega-3 plasmalogens in the morning and my mitochondrial support supplements, my omega-9s at night, and my support program there. Basic resistance training, maintaining strength, okay, push-ups, deep knee bends, dumbbells, maintaining skeletal muscle mass is critical. Also, just maintaining a positive service mindset. I think this concept of self-help, where people say, how important you are and how, you should have this self-esteem mindset. And I just think that sets people up to feeling that they deserve a whole lot more. And if you kind of dedicate your life to service, in a sense, like you're here to help and I'm not here to try to build an island and that kind of stuff, that creates a sense of peace in your world. And you can kind of get up in the morning, do your work, and create a level of purpose that never ends. Okay, so if you help others, if your purpose is actually to help others and understand and incorporate that, then that never ends. Okay, there's no end. So we talk about, as you get older, how do you maintain a level of purpose? And I think this is one of the concepts for me, is to get up every day and say, okay, every day is a new day. It's Groundhog Day. It's whatever accomplishments I made yesterday, those are done. Okay, what am I going to accomplish today? And then at the end of the day, I go to bed. And so those are the things that I think create some peace. Otherwise, you are always kind of comparing yourself to other things in this world, and really it doesn't really matter. And I think that for me, if you maintain your biochemical support structure, maintain your community, for me, my community is all my staff and employees and my family and all the things that we do. And then just kind of make sure you're pushing yourself just enough that you can overcome it, but not too much that you feel like you have to shut down and find a rock to hide under.
Back to that healthy hormetic stress.
Yeah.
This was a 4-hour master class. I definitely feel like my brain went to the gym, and I'm sure others do as well. So thank you so much for your work, for creating new tools and new approaches to healing for all of us. Thank you for being a light in this world. It's an incredible pleasure to have the opportunity to interview you and to learn from you. So thank you so much, Dr. Goodenowe.
Well, thank you, Scott. And we'll see you again soon.
Thank you for listening to today's episode of the Better Health Guy podcast. You can learn more about today's guest, including relevant links and resources, in the show notes. This podcast may provide community discounts and occasionally share links from affiliate partners. You can find this and other episodes on YouTube, Spotify, Apple Podcasts, Amazon Music, iHeart, and more. To learn more about Scott's personal journey to better health, visit BetterHealthGuy.com. Join us next time on the Better Health Guy podcast.